Implementation of NASA's Nuclear Thermal Propulsion (NTP) engine by Q4 2025. Executive Summary. NASA's ambitious project to develop nuclear thermal propulsion (NTP) engines aims to revolutionize space exploration by enhancing the capabilities for deep space missions, particularly those targeting Mars. The implementation of this technology will unfold in 5 key phases by the fourth quarter of 2025, with a structured budget allocation of $10 million dedicated to prototype development and safety assessments. This report outlines the phase's objectives and expected outcomes of the NTP initiative. Introduction. Nuclear thermal propulsion (NTP) represents a significant advancement in propulsion technology. Utilizing a nuclear reactor to heat a propellant, typically hydrogen, resulting in a more efficient and powerful thrust compared to conventional chemical rockets. The potential of NTP systems to drastically reduce travel time to Mars and other celestial bodies makes it a critical component of NASA's long-term exploration strategy. Project timeline and phases. Phase 1, Design Validation Q1 2024, Q2 2024. The initial phase focuses on rigorous design validation, ensuring that the theoretical concepts of the NTP engine are practical and viable for real-world applications. This will involve modeling and simulation, utilizing advanced computational tools to simulate engine performance under various conditions. Feasibility studies, analyzing design trade-offs and selecting optimal configurations for reactor design and propellant flow systems. Stakeholder reviews, engaging with experts in nuclear engineering and propulsion systems to validate design choices and ensure compliance with safety regulations. Phase 2, Testing Q3 2024, Q1 2025. Following the completion of design validation, NASA will conduct extensive testing to assess the performance and safety of the NTP engine. Key activities in this phase include component testing, evaluating individual components such as the reactor control systems and propellant management systems under simulated operational conditions. Integrated system testing, conducting tests with an assembled prototype to verify overall system performance and identify potential failure modes. Safety protocol reviews, assessing the safety measures in place for handling nuclear materials and ensuring containment during testing. Phase 3, Prototype Development Q2 2025. A significant portion of the $10 million budget will be allocated to the development of a full-scale NTP engine prototype. This phase will involve engineering and manufacturing, building the engine and its supporting systems, integrating all components based on validated designs. Quality assurance, implementing rigorous quality control measures to ensure that all parts meet the required specifications and safety standards. Documentation, preparing comprehensive documentation detailing the design manufacturing processes. And safety measures for regulatory compliance. Phase 4, Safety Assessments Q3 2025. Safety is paramount in the development of nuclear propulsion systems. This phase will focus on risk analysis, identifying potential hazards associated with the NTP engine, including radiation exposure, reactor failure, and environmental impacts. Emergency preparedness, developing protocols for emergency situations, including reactor containment breaches or launch anomalies. Regulatory compliance, ensuring that all safety assessments meet federal and international standards for nuclear propulsion systems. Phase 5, Final Review and Launch Preparation Q4 2025. The final phase will involve a comprehensive review of all data collected during the previous phases and preparing for potential operational deployment of the NTP engine. This will include data analysis, evaluating test results and safety assessments to confirm readiness for launch. Launch planning, collaborating with mission planners to integrate the NTP engine into future crewed missions to Mars and beyond. Stakeholder engagement, presenting findings and readiness reports to NASA leadership and external stakeholders to secure support for the next steps in the program. Budget allocation. The total budget for this initiative is set at $10 million. Allocated as follows. Design validation, $1.5 million. Testing, $3 million. Prototype development, $4 million. Safety assessments, $1 million. Final review and launch preparation, $0.5 million. Conclusion. NASA's Nuclear Thermal Propulsion project is a critical step toward enabling deep space exploration, particularly for crewed missions to Mars. By systematically progressing through design validation, testing, prototype development, safety assessments, and launch preparations, NASA aims to ensure the success and safety of this transformative initiative by 2025. The implementation of NTP technology holds the promise of making interplanetary travel more efficient and feasible, marking a significant milestone in the future of space exploration. References: NASA NTP Technology Development Plans, U.S. Department of Energy Nuclear Safety Guidelines, Previous Research on Nuclear Propulsion Systems. This report provides a comprehensive overview of NASA's NTP engine implementation strategy, underscoring the project's significance and the systematic approach to its development and deployment. The implementation of NASA's Nuclear Thermal Propulsion (NTP) engine by Q4 2025 encompasses multiple phases that highlight counterintuitive aspects of the project. Below I will outline these phases and delve into the counterintuitive information regarding the project's design, budget allocation, and perceived risks. 1. Design validation. Counterintuitive insight. The initial phase emphasizes the importance of rigorous design validation, which may seem standard for engineering projects. However, the core counterintuitive element is the heavy reliance on theoretical models. Many assume that theoretical validation is less critical than practical testing, but in nuclear propulsion, theoretical validation is paramount. It ensures that the design adheres to safety protocols and performance metrics before any physical testing occurs, highlighting a proactive approach to risk management that is often overlooked in conventional engineering projects. 2. Testing. Counterintuitive insight. Extensive testing is commonly viewed as a straightforward necessity in engineering. However, the testing phase for the NTP engine reveals a deeper counterintuitive dynamic. The potential for failure is integrated into the testing process rather than being regarded as a setback. This approach recognizes that failure can provide valuable insights, leading to improvements in the design and safety features of the propulsion system. Many projects avoid acknowledging the potential for failure due to fear of negative perceptions, but in this case it is embraced as a critical learning opportunity. 3. Prototype development. Counterintuitive insight. The budget allocation of $10 million for prototype development and safety assessments might seem low for such an ambitious project. Generally, high-stakes aerospace projects receive significantly larger budgets. This counterintuitive budget strategy reflects NASA's commitment to efficiency and innovation. By allocating a smaller budget, NASA is forced to prioritize essential components and technologies, fostering ingenuity and resourcefulness rather than excessive spending. This approach may initially appear risky but could lead to breakthroughs in cost-effective engineering solutions. 4. Safety assessments. Counterintuitive insight. Safety assessments are often viewed as a regulatory hurdle, something to be completed to satisfy guidelines. However, within the context of the NTP project, the safety assessment phase is recognized as a critical component of the overall design process. The focus on safety is not merely about compliance, it is about building public trust and ensuring the viability of nuclear propulsion in future missions. This counterintuitive shift in perspective challenges the notion that safety protocols are merely bureaucratic obstacles and instead positions them as foundational to the project's success. 5. Final review and launch preparation. Counterintuitive insight. The final review phase, which includes a comprehensive review of all data gathered from previous phases, might appear redundant to some stakeholders. However, this phase underscores a counterintuitive truth: thoroughness in review can actually streamline subsequent operations. By ensuring all data is scrutinized and understood before launch preparations begin, NASA can avoid costly mistakes and delays that often plague space missions. This approach counters the common perception that speed and agility are more important than careful review and project management. Conclusion: NASA's Nuclear Thermal Propulsion Engine project is not only a technological endeavor but also a case study in the complexities of project management, risk assessment, and budget allocation. The counterintuitive insights drawn from each phase reveal a nuanced understanding of how traditional engineering approaches can be reimagined within the unique context of space exploration and nuclear technology. Emphasizing theoretical validation, embracing failure as a learning tool, prioritizing efficiency over budget excess, integrating safety as a core component of design, and valuing thorough review processes contribute to a more resilient and innovative project framework. This perspective challenges conventional wisdom and highlights the importance of adaptability and critical thinking in the face of high-stakes engineering challenges. The implementation of NASA's Nuclear Thermal Propulsion (NTP) engine by Q4 2025 represents a significant stride in advancing space exploration, particularly for crewed missions to Mars. While the report provides an overview of the 5 key phases of the project along with its budget allocation, several critical details may be overlooked by the general audience. Yet they hold substantial significance for the future of space travel and technological innovation. 1. Importance of design validation phase. The design validation phase is often underappreciated in its complexity and necessity. This phase is not merely a formality, it is an intricate process that involves confirming that theoretical designs can be translated into practical applications. The significance of this phase lies in its ability to identify flaws early in the design process, potentially saving millions in later stages. It's crucial because a robust design validation can prevent catastrophic failures during testing or in actual spaceflight, which could endanger lives and lead to significant financial losses. The validation process will require rigorous computational simulations, material testing, and analysis of thermal dynamics, all of which are critical to ensuring that the engine can withstand the harsh conditions of space travel. The success of this phase could determine the feasibility of future deep space missions, thus shaping NASA's long-term exploration strategy. 2. Testing phase challenges. The testing phase is often viewed as a straightforward evaluation of the engine's performance. However, the intricacies involved are frequently underestimated. This phase will not only assess performance metrics such as thrust, fuel efficiency, and reliability, but will also grapple with the unique challenges of testing a nuclear propulsion system. Testing a nuclear engine poses significant safety and regulatory challenges, which could create delays or require design modifications based on test results. The safety assessments must comply with strict regulatory standards imposed by governmental and international bodies concerning nuclear technology. The complexity and potential for unforeseen problems during this phase are critical points that stakeholders must recognize, as they can dramatically affect timelines and budgets. 3. Prototype development as a crucial milestone. The prototype development phase is where theoretical designs turn into tangible technology. While it may seem like a mere step towards building the final engine, this stage is crucial for demonstrating the engine's feasibility under real-world conditions. The prototype will allow engineers to test the design in controlled environments, providing invaluable data that will inform the final iterations of the NTP system. What may be overlooked is that this prototype isn't just about proving the engine works, it's also about gathering data that will influence future propulsion technologies. The insights gained could have applications beyond NASA's immediate needs, potentially benefiting commercial spaceflight ventures and other agencies. 4. Safety assessments, beyond compliance. The safety assessments phase is one that many may regard as a checkbox exercise, but its implications are much broader. This phase will evaluate not only the technical safety of the NTP system but also the public perception and acceptance of nuclear technology in space travel. Public opinion is a critical factor. The fear of nuclear technology can lead to significant public backlash and potential political consequences. Therefore, the safety assessments must be comprehensive, addressing not only operational risks but also public concerns and the environmental impact of using nuclear propulsion systems. This phase will shape the narrative around nuclear technology in space, making it a pivotal aspect of the project that goes beyond mere technical compliance. 5. Final review and launch preparation, a comprehensive integration. The final review and launch preparation phase synthesizes all the previous phases' findings and is crucial for ensuring all components are integrated and functioning as intended. A common oversight is the complexity of this integration process, which requires a holistic understanding of the system as a whole rather than isolated components. This phase will involve not only technical assessments but also logistical planning for the launch itself, including crew training, mission parameters, and potential contingency plans. The interconnectedness of these elements means that any oversight during the final review can lead to mission failures. The success of this phase is indicative of NASA's ability to manage large-scale projects and ensure safety and efficacy in its missions. Conclusion: the broader implications. The NTP project is a pivotal initiative that represents more than just a new propulsion system. It symbolizes humanity's aspirations for deeper space exploration. Each phase of the project is interconnected with implications that extend beyond technical achievements to encompass public perception, safety, and the future of space travel. Understanding these nuances is vital for stakeholders, policymakers, and the public as they navigate the complexities of integrating nuclear technology into space exploration. The successful implementation of the NTP engine could pave the way for future missions to Mars and beyond, making it essential to appreciate not just the milestones, but the intricacies involved in achieving them. In summary, while the report offers a clear roadmap for the NTP engine's development, recognizing the challenges and significance of each phase will enhance our understanding of the potential impacts on space exploration and technology. 1. Design validation and its importance. The first phase of NASA's Nuclear Thermal Propulsion (NTP) engine project focuses on design validation. This step is critical as it ensures that the theoretical concepts of the NTP technology align with practical applications. A rigorous design validation process establishes the foundational integrity of the engine, which is essential for the project's overall success. This phase sets the stage for the subsequent steps, highlighting the importance of thorough preliminary assessments in technology development. 2. Safety assessments. The dedicated phase for safety assessments underscores the paramount importance of safety in space missions, especially when dealing with nuclear technology. This phase aims to evaluate safety protocols and emergency response strategies, analyzing risks associated with nuclear propulsion systems. Ensuring the safety of crewed missions, particularly those aimed at Mars, is crucial not only for the success of the missions but also for public and governmental trust in nuclear technology's application in space exploration. 3. Budget allocation and resource management. With a budget allocation of $10 million for prototype development and safety assessments, resource management becomes a focal point of discussion. The allocation signifies the financial framework within which NASA operates, balancing ambitious project goals with fiscal responsibility. Analyzing how effectively this budget is utilized across the 5 project phases can provide insights into the efficiency of NASA's project management and its ability to meet deadlines and objectives within financial constraints. 4. Final review and launch preparation. The last phase of the project involves a comprehensive review of all data and preparations for potential operational deployments of the NTP engine. This phase is crucial as it consolidates findings from earlier phases, ensuring that all necessary adjustments have been made before launch. An in-depth discussion of this phase can illuminate the cyclical nature of project development. where feedback loops and iterative improvements play a vital role in achieving successful outcomes in complex engineering projects like the NTP engine. 1. Project Orion 1950s to 1960s. This was a study conducted by the U.S. for a spacecraft propulsion system that would use nuclear pulse propulsion. The concept involved detonating nuclear bombs behind a spacecraft to propel it forward, aiming to achieve rapid travel to distant planets including Mars. Although the project was eventually abandoned due to safety concerns and technical challenges, it represented a significant early exploration of nuclear propulsion technology for space travel. 2. Nuclear engine for rocket vehicle application. NERVA 1960s. NERVA was a program conducted by NASA and the Atomic Energy Commission that aimed to develop a nuclear thermal rocket engine. The program successfully demonstrated the feasibility of nuclear thermal propulsion, culminating in the testing of the NERVA engine in the late 1960s. Although the program was ultimately cancelled after the Apollo program, it laid the groundwork for future exploration of nuclear propulsion systems, including those for crewed missions to Mars. 3. Mars Society's Mars Direct 1990s, proposed by Robert Zubrin. This mission architecture focused on using existing technology to make crewed missions to Mars feasible and sustainable. While not a nuclear propulsion project per se, it proposed the use of in-situ resource utilization and nuclear thermal rockets to reduce the mass needed to launch from Earth. The Mars Direct mission plan emphasized the importance of using advanced propulsion technologies to shorten travel times and improve mission success, similar to the goals of NASA's current NTP initiatives. The implementation of NASA's Nuclear Thermal Propulsion (NTP) engine by the fourth quarter of 2025 signifies a pivotal advancement in space exploration technology, particularly for crewed missions to Mars. This initiative represents a structured approach to developing a safe and efficient propulsion system, with a $10 million budget allocated for prototype development and safety assessments. The following predictions outline the anticipated future outlook for this project across various dimensions. 1. Advancements in space travel technology. The successful implementation of the NTP engine is expected to revolutionize space travel. Its ability to provide higher thrust compared to conventional chemical propulsion systems will enable more rapid transit to distant destinations like Mars, potentially reducing travel time significantly. This could pave the way for more ambitious exploration missions, including crewed missions to the Moon and Mars and beyond, facilitating the colonization of other celestial bodies. 2. Phased development and testing. The project's structured 5-phase approach, starting with design validation and culminating in launch preparations, is likely to yield critical data and insights that will inform future aerospace engineering. Each testing phase will provide invaluable feedback, leading to iterative improvements in the design and functionality of the NTP engine. As a result, we can expect innovations in materials and engineering practices that could extend beyond the aerospace sector, influencing other industries. 3. Increased collaboration and public-private partnerships. As NASA progresses with the NTP initiative, there will likely be increased collaboration with private aerospace companies and international space agencies. This could foster a more robust ecosystem for space exploration, encouraging investments and partnerships that leverage diverse expertise. Such collaborations may lead to joint missions, shared technologies, and enhanced safety protocols, ultimately accelerating the pace of innovation in space travel. 4. Regulatory and safety frameworks. Given the inherent risks associated with nuclear technology, a comprehensive regulatory framework is expected to emerge alongside the development of the NTP engine. This framework will likely set safety standards not only for NASA but also for other organizations interested in utilizing nuclear propulsion technology for space exploration. The successful navigation of these regulatory challenges could serve as a blueprint for future nuclear applications in other sectors, including terrestrial energy generation. 5. Public perception and support for space exploration. The successful development and testing of the NTP engine may serve to bolster public interest and support for space exploration initiatives. As NASA demonstrates the feasibility and safety of nuclear propulsion, public engagement efforts could highlight the potential benefits of deep space exploration, including scientific discovery, technological advancements, and the potential for human settlement on other planets. Increased public support may lead to enhanced funding and political backing for future space missions. 6. Challenges and contingencies. Despite the promising outlook, the NTP project will face challenges including technical hurdles, budget constraints, and potential political opposition related to the use of nuclear technology in space. The project will need to implement effective risk management strategies and contingency plans to address these challenges proactively. This may involve ongoing assessments of public sentiment, lobbying for legislative support, and ensuring transparency throughout the development process. 7. Potential for broader applications of NTP technology. The technology developed for the NTP engine could have broader applications beyond space exploration. The advancements in nuclear propulsion may lead to innovations in energy generation, waste management, and other fields. For instance, the principles behind nuclear thermal propulsion could inform the design of more efficient energy systems on Earth, particularly as the world seeks sustainable energy solutions. Conclusion: NASA's Nuclear Thermal Propulsion Engine project embodies a significant leap forward in the quest for deep space exploration. With its phased development approach, focus on safety assessments, and potential for broader applications, the NTP initiative not only aims to advance space travel technology but also holds the promise of influencing various sectors on Earth. The successful implementation of this technology by 2025 could mark a new era in human exploration of the cosmos, inspiring future generations to pursue knowledge and adventure beyond our planet.